The universe was not supposed to grow up this fast. According to everything we thought we understood, the early cosmos should have been dim, chaotic, and simple, a fog of hydrogen waiting patiently for structure. Instead, James Webb looked back more than 13 billion years and found galaxies already massive, already organized, already shining like they had skipped childhood entirely. Entire cities of stars standing where there should have been campfires. The biggest telescope ever built has opened a window into the cosmic nursery, and what we're seeing looks less like infancy and more like something that matured in secret. We used to imagine the early universe as a slow builder. After the Big Bang, space expanded, cooled, and settled into darkness. Gravity, patient and relentless, began pulling gas together. Small clumps formed first, then slightly bigger ones. Over hundreds of millions of years, those clumps merged into primitive galaxies. That was the script. Slow assembly, gradual growth, cosmic toddler years stretching across eons. But when Webb unfolded its gold mirrors 1 million miles from Earth and turned its infrared eyes toward the deepest darkness, we expected faint smudges, tiny things, the earliest sparks. Instead, we saw structures so large they force us to blink twice. Galaxies as massive as the Milky Way appearing when the universe was less than 400 million years old, barely 3% of its current age. To put that into something we can feel, imagine a human baby lifting a car, not struggling, just capable. That is the scale of the surprise. We are looking at light that left those galaxies when Earth did not exist, when the Sun did not exist, when even most heavy elements had not yet been forged. And yet these galaxies already contain billions of stars. Billions. Each star a furnace hotter than any explosion humanity has ever made. Each star contributing to a system large enough to bend space-time itself. The universe did not ease into complexity. It appears to have accelerated into it. And the deeper we look, the stranger it becomes. Webb's power comes from infrared vision. As the universe expands, ancient light stretches its wavelengths pulled longer, redder, fainter. What began as brilliant ultraviolet starlight arrives here as heat signatures. Webb was designed to catch that stretched glow, to see through cosmic dust and backward in time. And when it did, it found galaxies already structured disks, spirals, even hints of bars and clusters at epochs when theory predicted chaotic blobs still in formation. We thought gravity needed more time. The early universe was dense, yes, but also expanding violently. Matter racing outward, everything thinning. Structure should have struggled to assemble under those conditions. There simply shouldn't have been enough time for gas to cool, collapse, ignite, merge, stabilize. And yet there they are. When we stare at those images, we're not just seeing distant galaxies. We're witnessing a challenge to our timeline, a suggestion that the cosmic clock may tick differently than we assumed. Picture standing on a shoreline, watching waves roll in at a predictable rhythm. You've measured them, modelled them, written equations describing their behaviour. Then one day, a wave arrives twice as tall, twice as fast, and the ocean insists it has always been capable of this. That is what Webb has done. It has shown us that the early universe may have formed stars at breakneck speed, converting primordial hydrogen into blazing stellar engines far more efficiently than our simulations allowed. Some of these early galaxies appear packed with stars so densely that they rival modern ones. That means star formation rates that border on violent, whole regions igniting simultaneously, gravity pulling gas inward with ruthless efficiency. And somewhere inside those newborn galaxies, something even more extreme may have been forming. Supermassive black holes. We already knew that nearly every large galaxy today contains one, including ours. At the centre of the Milky Way sits Sagittarius, a star, a black hole 4 million times the mass of the Sun. But Webb has found evidence that enormous black holes existed astonishingly early, some weighing millions or even billions of solar masses when the universe was still in its first few 100 million years. To grow that large requires feeding gas spiraling inward, compressing, heating, radiating energy before crossing the event horizon. That process takes time, or at least we thought it did. But the early universe may have been less patient. Imagine compressing the mass of 1 billion suns into a region smaller than our solar system in less time than it took Earth's continents to form. That is the scale of what we're confronting. If black holes formed earlier, if galaxies assembled faster, if stars ignited sooner, then the cosmic dawn was not a gentle sunrise, it was a flash. We are forced to reconsider the first few 100 million years not as a quiet build-up, but as a period of furious creation, hydrogen collapsing into stars, stars exploding into heavier elements, galaxies merging, colliding, rearranging, black holes swallowing and shaping everything around them, all before our own sun was even a thought. And here's what makes it visceral. Every atom in your body heavier than hydrogen was forged in stars like those. Carbon in your cells, oxygen in your lungs, iron in your blood. Those elements did not exist at the beginning. They had to be created through fusion, through collapse, through explosion. If stars were forming earlier and faster than expected, then the ingredients for planets and eventually life were being prepared sooner than we imagined. The timeline shifts. The window opens wider. We are no longer asking only how the universe formed structures. We are asking how quickly it became capable of complexity. Webb's images are not just beautiful, they are confrontational. They suggest that the cosmos may be more efficient, more dynamic, more aggressive in its self-organization than we allowed. Gravity may not be a slow sculptor. It may be a sudden architect. And as we continue to stare deeper, pushing closer to the moment when the first stars ignited, we approach a threshold. Because if galaxies existed this early, structured and massive, then what preceded them may be even more extreme than we dared to model. The first stars, the first black holes, the first light tearing through primordial darkness. We are not just looking back in time. We are watching the universe reveal that it may have grown up faster than we ever expected, and that means something fundamental about how reality builds itself may still be waiting just beyond our current horizon. Before there were galaxies, there was darkness so complete it makes our deepest night look bright. For hundreds of millions of years after the Big Bang, the universe expanded and cooled into a vast, invisible ocean of hydrogen and helium. No stars, no planets, no glowing spirals, just matter smooth, nearly uniform, stretched across distances so immense that even light took ages to cross them. We call it the cosmic dark ages. If you had somehow existed, then suspended in that early void, you would have seen nothing. No points of light, no horizon, just blackness in every direction. The temperature would have been warmer than today's space, but still frigid beyond human survival. And yet, inside that darkness, gravity was already working. Tiny ripples in density differences smaller than 1 part in 100,000 had been imprinted during the universe's first moments. Barely measurable fluctuations in the afterglow we now call the cosmic microwave background. Those ripples were the seeds. Gravity began tugging on them immediately. Where matter was slightly denser, it pulled in more matter. Where it pulled in more matter, it grew stronger. Over time and in cosmology, time means tens to hundreds of millions of years, these subtle imbalances amplified. We expected this growth to be steady, incremental, small halos of dark matter forming first invisible scaffolds composed of a substance we still cannot directly see. Ordinary gas would fall into those halos, compress, heat, and eventually ignite into the first stars. That ignition was supposed to be rare at first, isolated, fragile. Instead, Webb is hinting that when the lights came on, they came on fast. The first stars known as population 3 stars were not like our Sun. They were enormous, hundreds of times more massive, made almost entirely of hydrogen and helium. With no heavy elements to cool them efficiently, they grew huge before collapsing under their own gravity. And huge stars live fast. While our sun will shine for about 10 billion years, these primordial giants likely burned for only a few million before exploding as supernova detonations so powerful they briefly outshone entire galaxies. Imagine a star 100 times the mass of the sun collapsing and exploding before Earth would have even formed. That was the universe's first forge. Those explosions seeded space with heavier elements: carbon, oxygen, silicon, iron, the raw materials for planets and life. But more than that, they injected energy into their surroundings. They reionized the universe, blasting apart neutral hydrogen atoms, making the cosmos transparent to ultraviolet light again. The fog began to lift. This era cosmic reionization marks the transition from darkness to a universe filled with light. We thought it unfolded gradually over hundreds of millions of years. Webb suggests it may have surged. Some of the galaxies it has detected appear bright enough, massive enough, to contribute significantly to reionization much earlier than models predicted. That means star formation wasn't a trickle. It was a flood. Picture dry grassland under a sky full of sparks. We expected a few scattered flames. Instead, whole regions may have ignited nearly simultaneously. And these early galaxies weren't just small gatherings of stars. Some seemed compact but extraordinarily dense, packing stellar mass into volumes far tighter than modern galaxies of similar weight. They are like cosmic pressure cookers, gas collapsing inward rapidly, stars forming in bursts so intense they reshape their own environment. Gravity, in the early universe, had an advantage. Everything was closer together. The average density of matter was far higher than it is today. Galaxies didn't need to reach across millions of light years to interact. They were neighbours in a tighter cosmic neighbourhood. Collisions and mergers would have been common. When galaxies merge, their gas clouds collide, compress, and trigger explosive star formation. We see this in the modern universe, starburst galaxies glowing from furious stellar birth. Now imagine that process happening everywhere, in a universe only a few 100 million years old. It would look chaotic, brilliant, violent. And inside that violence, black holes would feed. When massive stars died, some collapsed directly into black holes tens or hundreds of times the sun's mass. If they formed in dense regions packed with gas, they could grow quickly, swallowing matter at rates limited only by radiation pressure pushing back. Under normal conditions, there's a limit, the Eddington limit, governing how fast a black hole can grow before its own energy output chokes off infall. But if early gas clouds were dense and turbulent enough, that limit may have been briefly exceeded. Or perhaps some black holes formed not from stars at all, but from direct collapse, entire gas clouds imploding into black holes, tens of thousands of solar masses from the start. If that happened, then the supermassive black holes Webb is seeing in the early universe didn't start small. They started ambitious. We are confronting the possibility that the first structures were not timid, that the early cosmos did not hesitate. And here's where we feel it. Our own galaxy took billions of years to evolve into its current spiral form. The Sun is a second or third generation star, born from material enriched by earlier stellar generations. Earth formed 4.5 billion years ago, long after those primordial galaxies had already lived through dramatic transformations. When Webb peers back 13.4 billion years, we are seeing systems already mid-story, already complex, already sculpted. It compresses our sense of cosmic time. The gap between the Big Bang and organized galaxies once imagined as a long adolescence may instead have been a rapid growth spurt, a universe sprinting towards structure. And the deeper Webb looks, the more this pattern holds. Every new ultra-deep field image contains tiny red points, each one a galaxy so distant its light is stretched into infrared. Some of them challenge our mass estimates, some appear chemically mature, some suggest that star formation was not only early, but efficient beyond expectation. The universe seems reluctant to remain simple. There is something deeply unsettling and thrilling about that, because it suggests that complexity is not fragile, it is not rare, it may be an almost inevitable outcome when gravity and time collaborate. And we are only at the beginning of this new view. Webb has not yet reached its limit. It is pushing closer to the first 200 million years, closer to the moment when the first stars flickered on. If galaxies were already mature by 300 or 400 million years, then what was happening at 150? At 100? At 50? We are moving toward a boundary where light itself was just beginning to exist in recognizable form. And the next layer may force us to rethink not just how fast galaxies formed, but whether our understanding of the early universe's ingredients is complete at all. There is a number that quietly governs everything we're talking about. 13.8 billion years. That is the age of the universe, the time since space itself expanded from an ultra-dense, ultra-hot beginning. Every galaxy, every star, every atom in your body has existed somewhere inside that expanding timeline. Now compress it. If the entire history of the universe were a single calendar year, the Big Bang would happen at midnight on January 1st, the Milky Way would begin forming in early spring, the Sun would ignite in early September, dinosaurs would arrive on December 25th, humans would step onto the scene in the final minutes before midnight on December 31st. And the galaxies James Webb is now seeing, they appear in January. Not late January, not even mid-January. In the first few days, that is the dissonance. We expected structure to emerge slowly, like frost spreading across glass. Instead, it may have crystallized almost immediately. To understand why this matters, we have to step into the first few minutes after the Big Bang, when the universe was still a seething plasma, protons and electrons flying freely, light trapped in a blinding fog, temperatures in the billions of degrees, matter and radiation coupled tightly together. After about 380,000 years, which in cosmic terms is barely a breath, the universe cooled enough for electrons and protons to combine into neutral hydrogen. Light finally escaped. That ancient light still fills the cosmos today as the cosmic microwave background. At that moment, the universe became transparent. But transparent does not mean structured. It was still nearly uniform, smooth, featureless on large scales. The tiny fluctuations imprinted in that radiation measured with exquisite precision by missions like Planck told us something critical. The early universe's density variations were small, extremely small. And small fluctuations grow slowly. Gravity needs time. So our simulations, fed with those initial conditions, produced a predictable story. Dark matter collapses first into halos, gas follows. The first stars ignite after perhaps 100 to 200 million years. Galaxies build gradually through mergers and accretion. Massive galaxies take billions of years to assemble. Webb is whispering that this growth curve may be steeper. Some candidate galaxies detected at redshifts above 10, meaning we are seeing them as they were within 400 million years of the Big Bang, appear to contain stellar masses approaching billions of suns. That requires extraordinary efficiency. To build a billion solar masses of stars, you must gather gas, cool it, compress it, ignite it, and avoid blowing it all back out through supernova explosions and radiation pressure. That balancing act is delicate even today. Yet early galaxies seem to have managed it almost immediately. One possibility is that we underestimated how quickly gas could cool and collapse in dense primordial halos. Another is that the initial dark matter structures were more conducive to rapid assembly than our models assumed. There's also the question of dark matter itself. We cannot see it directly. We infer its existence because galaxies rotate too fast to be held together by visible matter alone. Gravitational lensing. The bending of light around massive clusters reveals more mass than we can account for in stars and gas. Cosmic structure formation models rely on dark matter as the scaffolding. If galaxies formed earlier than expected, perhaps that scaffolding behaved slightly differently in the early universe. Not dramatically different, not enough to overthrow everything, but subtly enough to accelerate collapse. And then there is feedback. When stars form, they don't do so quietly. Massive stars emit intense ultraviolet radiation, carve out ionized bubbles in surrounding gas, and explode as supernovae. That energy can halt further star formation by heating and dispersing gas. We believed early star formation would self-regulate bursts followed by suppression, but what if, under the extreme densities of the young universe, gas inflow outpaced feedback? What if gravity simply overwhelmed the blowback? That would create sustained, rapid star formation. And Webb's data hints at galaxies with precisely that behaviour. Now imagine standing on a planet that does not yet exist, orbiting a star that has not yet formed, inside a galaxy that will not assemble for billions of years, and realizing that across the cosmos, entire stellar metropolises are already blazing. It compresses our sense of origin. The elements in your bones were forged in stars. Those stars required previous generations to create heavy elements. The earlier galaxies begin forming, the sooner chemical complexity spreads. If star formation ignited aggressively within the first few 100 million years, then the universe began manufacturing the ingredients of life almost immediately. Not leisurely, urgently. This does not mean life existed then. The environment was violent radiation intense, galaxies colliding frequently, supernovae detonating constantly. But the chemical groundwork may have been laid far earlier than our intuition allowed. There is something profound about that acceleration. We often imagine the universe as ancient and slow, vast and patient. But what Webb is revealing suggests that once conditions were right, structure erupted quickly. It's like watching condensation form on cold glass. For a long time, nothing seems to happen. Then suddenly droplets appear everywhere at once. The early universe may have crossed a threshold. And once crossed, gravity did not hesitate. What makes this even more extraordinary is that we're seeing this with unprecedented clarity, because Webb is operating at the edge of physical possibility. Its 6.5-meter segmented mirror collects faint infrared light that has travelled for more than 13 billion years. Its instruments measure redshift, the stretching of wavelengths caused by cosmic expansion, allowing us to determine how far back in time we're looking. Each deep field image is not just a picture. It is a time slice. And in these slices, we're discovering that our timeline might have been conservative. The universe may have reached adolescence faster than we thought. But the story does not end with early galaxies. Because if structures formed quickly, then the first gravitational giants, the earliest black holes, may have emerged in parallel, and their presence would reshape everything around them. Black holes do not just consume, they regulate. Their jets can heat gas across entire galaxies. Their gravity can orchestrate stellar motion. Their growth and the growth of galaxies appear intertwined even today. If supermassive black holes were already massive in these early systems, then something extraordinary happened in the first few 100 million years. Something efficient. Something powerful. We are not watching a hesitant cosmos. We are watching a universe that may have sprinted into complexity assembling stars, galaxies, and black holes with startling speed. And the closer Webb pushes toward the first light, the more it feels like we are approaching a threshold where the assumptions we carried for decades begin to loosen. Not collapse. Loosen. Because the universe is not contradicting physics. It is revealing that we may not yet have fully understood how aggressively physics can act when conditions are extreme. There is a moment in every cosmic story where scale becomes suffocating. This is that moment. Because if galaxies were already massive within 300 to 400 million years after the Big Bang, then somewhere before that in an even tighter, hotter universe matter was collapsing with astonishing speed. Let's shrink it down. When the universe was 100 million years old, it was roughly 1/14 its current size. Galaxies were not separated by millions of light years the way they are now. Everything was closer, denser. Gravity had less distance to conquer. Density is power, The average density of matter in the universe decreases as space expands. Roll the clock back, and that density climbs dramatically. Gas clouds were thicker, dark matter halos more compact. The raw ingredients for collapse were not thinly scattered, they were packed. Under those conditions, the time it takes for gravity to pull material together, what physicists call the freefall time, shortens. Collapse accelerates. Imagine rain falling into a shallow pond versus rain falling into a deep canyon. In the canyon, water gathers faster, funnels harder, and pressure builds more violently. The early universe was that canyon. And once gas begins collapsing, it heats. If it can cool efficiently, it keeps collapsing. If it cannot cool, pressure pushes back and slows the process. Here's the twist: primordial gas had fewer ways to cool. It lacked heavy elements like carbon and oxygen, which in modern galaxies radiate energy away effectively. So early star-forming clouds behaved differently. We assumed this inefficiency would slow star formation. But there's another possibility. If the gas clouds were massive enough, their gravity could overpower even inefficient cooling. Instead of fragmenting into many small stars, they might collapse into fewer, much larger ones, monstrous stars burning brighter and dying faster. These giants would flood their surroundings with radiation. When they exploded, they would inject heavy elements into nearby gas, suddenly improving cooling efficiency for the next generation. That creates a cascade. First-generation massive stars form quickly. They explode. Second-generation enriched gas cools faster, forming more stars. Repeat. In a universe that was already dense, this feedback loop could escalate rapidly. Webb's observations of surprisingly mature galaxies hint that such cascades may have happened earlier and more efficiently than our conservative models predicted. But the most dramatic acceleration may have involved something even more extreme. Direct collapse. Under certain conditions, instead of forming stars first, enormous gas clouds might have collapsed straight into black holes, skipping the stellar phase entirely. If a cloud tens of thousands of times the sun's mass implodes without fragmenting, it can create a massive black hole seed from the start. Not a remnant of a dying star. A gravitational abyss born full-grown. Such a seed would have a head start. Surrounded by dense gas in the early universe, it could feed rapidly, ballooning into a supermassive black hole within a few 100 million years. And Webb is detecting quasars, the brilliant beacons powered by feeding black holes at redshifts that imply they already existed astonishingly early. A quasar is not subtle. It can outshine its entire host galaxy. As matter spirals inward, friction and compression heat it to millions of degrees, producing radiation across the electromagnetic spectrum. Now picture that phenomenon when the universe is still in its infancy. Blazing cores punching through primordial darkness. These early quasars are not just curiosities, they are engines. Their radiation influences surrounding gas, possibly regulating star formation across vast regions. The early cosmos may have been an ecosystem of extremes gravity pulling inward, radiation blasting outward, galaxies colliding, black holes feeding, stars exploding. Not a quiet nursery, a crucible. And inside that crucible, the structure did not wait politely. It surged. There's another layer to this acceleration that makes it even more unsettling. When we look at distant galaxies, we're not seeing them directly as they are today. We're seeing their ancient light. But that light passes through intervening gas. It is absorbed and re-emitted. It carries fingerprint spectral lines that reveal chemical composition and ionization state. Webb's instruments can detect these fingerprints with remarkable sensitivity. Some early galaxies show evidence of surprisingly strong emission lines, indicators of intense star formation and energetic processes. The light is not faint and timid, it is vigorous. That suggests galaxies weren't just present early. They were active. And if they were active, they were shaping their environment, rionizing hydrogen, enriching intergalactic space with heavy elements, altering the thermal history of the universe. The timeline tightens further. Within a few 100 million years, the cosmos transitions from opaque plasma to structured galaxies with complex chemistry and central black holes. If we scale this to human development, it's as if a newborn not only walks within weeks, but builds cities. We feel small in that compression. Earth formed about 9 billion years after the Big Bang. By that time, galaxies had already merged countless times. Black holes had grown and regulated their hosts. Heavy elements were abundant enough to build rocky planets. All of our history unfolds in the final third of the cosmic story so far. And yet, the foundations, the structural skeleton of the universe may have been assembled almost immediately. This doesn't mean our previous understanding was wrong. It means it may have been incomplete. Our simulations rely on assumptions about cooling rates, feedback efficiency, dark matter distribution, and initial conditions. Webb's data is forcing refinements adjustments that make early structure formation more aggressive, more efficient. Physics still holds. Gravity still pulls. Light still stretches. But the universe may exploit those laws more dramatically than we assumed when everything was packed tighter and hotter. And this is only the beginning of Webb's reach. Every deeper observation increases the chance of finding something even earlier galaxies at redshifts 1520, perhaps beyond, pushing us closer to the era when the first stars ignited. We are approaching the edge of the observable dawn. And as we move toward it, the question grows sharper. If complexity emerged this quickly, what else did the early universe manage to assemble before we thought it could? Because somewhere beyond the galaxies we've already seen lies the moment when the first light pierced the dark, and that moment may hold the most extreme acceleration of all. There is a boundary in cosmic history where the universe stops being theoretical and starts becoming visible. We are moving toward it. Beyond a certain redshift, beyond a certain distance, we approach the era when the very first stars ignited. Not galaxies, not clusters, single, colossal stars tearing light out of hydrogen for the first time. Before that moment, the universe was dark in any way we would recognize. After it, reality changed permanently. Because once the first stars formed, they began rewriting the chemistry of existence. To understand how violently this shift may have happened, we have to stand at the edge of total darkness. Picture a universe filled with neutral hydrogen atoms, each a single proton orbited by an electron. No heavier elements, no carbon, no oxygen, no iron. Just the simplest atoms drifting in expanding space. Gravity slowly pulls this gas into dense pockets within dark matter halos. As the gas compresses, it heats, but without heavy elements. Cooling pathways are limited, the cloud cannot shed heat easily, and so it resists fragmenting into many small stars. Instead, it collapses into something enormous. The first stars may have been 100 and 200, even 300 times the mass of our Sun. To feel that scale, if our Sun were the size of a basketball, one of these primordial giants would be a small car. They would have burned with ferocious brightness, millions of times more luminous than the Sun, flooding their surroundings with ultraviolet radiation. And they would have lived briefly. Massive stars consume fuel at staggering rates. Fusion accelerates under immense core pressure. In just a few million years, a blink compared to the Sun's 10 billion year lifespan, they would exhaust their hydrogen and collapse. Some would explode as pair instability supernovae, completely tearing themselves apart, scattering heavy elements across space. Others would collapse into black holes, leaving behind gravitational seeds. Now imagine thousands of these giants forming across the early universe in rapid succession. Each one a torch in the dark. Each one altering its environment. When enough of them ignite, their ultraviolet radiation strips electrons from surrounding hydrogen atoms. The universe becomes ionized again, transparent to high-energy light. The fog lifts. This epoch of reionization is one of the great transitions in cosmic history. It marks the universe's second major transformation of light. Webb is giving us glimpses of galaxies that appear capable of driving this transition earlier than expected. Which means the first stars may not have been rare. lonely beacons. They may have been abundant. If so, the cosmic dark ages were shorter than we thought. And that has consequences, because every time a massive star exploded, it enriched the surrounding gas. The next generation of stars would form from material containing carbon and oxygen. Cooling becomes more efficient. Stars become smaller and longer lived. Planets become possible. The speed of this chemical evolution determines how quickly rocky worlds could begin to form. If early star formation was aggressive, then heavy elements spread through the cosmos sooner. That shifts the window for planet formation forward in time. It does not mean Earth formed earlier. It means the universe may have been capable of forming Earth-like worlds far sooner than we imagined. Now step back. Webb's deepest observations suggest galaxies with substantial stellar mass already present when the universe was less than 400 million years old. To achieve that, multiple generations of stars must have lived and died quickly, which implies the first generation ignited even earlier, perhaps within 100 to 200 million years of the Big Bang. That is breathtakingly fast. For comparison, the time between the extinction of the dinosaurs and today is about 66 million years. The time between the first stars igniting and entire galaxies assembling may have been only a few times longer than that. On a cosmic scale, that is not gradual. That is explosive growth. There is something deeply humbling in realizing that complexity, structure, chemistry, even the seeds of habitability may have emerged almost as soon as the universe physically allowed it. It suggests that once the fundamental forces were in place, once gravity and expansion settled into balance, the formation of structure was not a reluctant accident. It was a consequence. And we are built from that consequence. The iron in your blood forged in a star that died before the sun was born. The oxygen you inhale created in stellar cores long before Earth existed. If the first stars formed earlier and more frequently than we predicted, then the chain of creation that eventually led to you began almost immediately after cosmic darkness. The universe did not waste time, and yet we must be careful. Some of Webb's earliest galaxy candidates are still being analysed. Spectroscopic confirmations refine distance estimates. Stellar mass calculations depend on assumptions about star formation rates and dust content. As data improves, some early mass estimates may shrink. But even with adjustments, the trend remains provocative. There are more bright, distant galaxies than our conservative models anticipated. The early universe appears crowded, not with mature spiral galaxies like the Milky Way, but with compact, intensely star-forming systems already far along in assembly. And here's where it becomes almost poetic. The farther we look, the smaller these galaxies appear in angular-sized tiny red smudges in deep fields. But physically, they are anything but small. They are engines of transformation operating at the dawn of time. Light from them has travelled for more than 13 billion years to reach us. It began its journey before our galaxy finished assembling, before our sun ignited, before Earth cooled. And now it lands on a gold mirror orbiting the sun, designed by a species that evolved on a rocky planet forged from ancient stellar debris. We are not just observing the early universe. We are the early universe looking back at itself. If structure formed earlier than expected, if stars ignited sooner, if black holes grew faster than the narrative of cosmic evolution tightens, it becomes more urgent, more dynamic. The dark did not linger. The first light may have surged. And as Webb continues to peel back layers of time, we're approaching the moment when even those first giant stars had not yet ignited, when the universe was balanced on the edge of its first illumination. Somewhere just beyond our current horizon lies the instant when gravity won its first decisive victory over darkness. And when we finally see it clearly, we may realize that the cosmos has been moving faster than we ever gave it credit for. There is a dangerous assumption we've carried for decades, that the early universe was simple. Simple physics, simple chemistry, simple structure. But simplicity at extreme density does not stay simple for long. When the universe was only a few 100 million years old, it was smaller, hotter, and denser. Dark matter halos, invisible gravitational wells were assembling rapidly. Ordinary matter was pouring into them like water into sinkholes. In modern space, galaxies are separated by millions of light years. Collisions take billions of years to unfold. But early on, distances were compressed, encounters were frequent, mergers were common. And mergers change everything. When two young galaxies collide, their gas clouds slam into each other at hundreds of kilometers per second. Shock waves ripple outward, gas compresses violently, star formation ignites in bursts. Today, we see this in systems like the Antennae Galaxy's spectacular starburst regions, where thousands of new stars are born in clusters. Now imagine that environment scaled to the entire early universe. Not rare, routine. Webb's observations suggest that early galaxies may have grown through rapid merging and accretion, building mass much faster than isolated systems would allow. Each merger feeds central regions with fresh gas. Each influx triggers another wave of star formation. It becomes a compounding process. Growth feeding growth. But here's where it intensifies. At the centers of many galaxies lie black holes. In today's universe, there is a striking correlation between the mass of a galaxy's central black hole and the mass of its stellar bulge. They grow together. That relationship implies feedback, a regulatory dance between gravity and radiation. In the early universe, that dance may have been more chaotic. If black hole seeds formed quickly either from massive stellar remnants or direct collapse, they would sit at the centers of gas-rich, turbulent galaxies. As gas funnels inward, the black hole feeds. As it feeds, it radiates enormous energy. That radiation pushes outward. Jets of relativistic particles shoot from the poles at near light speed. Winds driven by intense heat sweep through the host galaxy. These processes can both trigger and suppress star formation. They can compress gas in some regions while clearing it out in others. In a dense early universe, such feedback loops could operate on shorter timescales. And Webb is finding signs of active galactic nuclei feeding black holes astonishingly early in cosmic history, which means the interplay between stars and black holes began almost immediately. This is not a quiet infancy. This is a self-regulating system emerging at high speed. And there's another force at work, cold streams. Simulations suggest that in the early universe, gas did not always trickle gently into galaxies. Instead, vast filaments of relatively cool gas, part of the cosmic web, could channel material directly into galactic centers. Think of highways of hydrogen stretching across space, funneling fuel into growing galaxies without first heating to extreme temperatures. These streams would provide a steady supply of star-forming material, sustaining rapid growth. If that process was more efficient than expected, it could help explain why Webb sees galaxies that appear too massive for their age. Because they were not starving. They were being fed. The cosmic web itself may have been delivering fuel faster than we accounted for. Step back and feel what this implies. Within a few 100 million years, the universe may have already established the large-scale scaffolding we see today, filaments of dark matter connecting nodes of galaxies, clusters forming at intersections, voids expanding between them. The grand architecture may have assembled early. We are used to thinking of the universe as ancient beyond comprehension, slow-moving, glacial in change. But on its larger scales, it may have set its structure quickly, then spent billions of years refining it. Webb's data is not rewriting gravity. It is revealing how aggressively gravity can operate when the conditions are extreme. And we are only sampling small patches of sky. Each deep field image is like drilling a narrow core sample into the cosmic past. Even in those tiny fields, we're finding more early massive galaxies than predicted. Which raises a subtle but profound question. Were our simulations underestimating something fundamental about the efficiency of early structure formation? Perhaps the answer lies in how gas fragments under primordial conditions. Perhaps it lies in dark matter's small-scale behavior. Perhaps early star formation was clumpier, more intense, more concentrated than we imagined. We are refining, not discarding. The equations still hold. General relativity still describes gravity. Nuclear fusion still powers stars. The expansion of space still stretches light. But the universe seems to have used those laws at maximum intensity when everything was compressed. There's a human instinct to equate age with maturity, to assume that something young must be simple. Webb is quietly dismantling that instinct on a cosmic scale. The universe at 300 million years old may already have hosted galaxies containing billions of stars. It may have housed black holes weighing millions of solar masses. It may have been chemically enriched far earlier than our cautious timeline suggested. And if that is true, then the path from primordial plasma to structured cosmos was not a slow crawl. It was a rapid climb. Consider this Earth formed 4.5 billion years ago. Life emerged relatively quickly after conditions stabilized. Complex multicellular life took billions of years more. Intelligence capable of building telescopes emerged only in the last few 100,000 years. Our development feels long to us. But compared to the early universe's sprint into structure, it is almost leisurely. The cosmos assembled galaxies before it was even a billion years old. And now, 13.8 billion years later, we are building instruments capable of witnessing that assembly. We are looking back at a time when the universe was raw, when gravity, radiation, and dark matter were sculpting reality at full force. And the more we look, the more it feels like we have underestimated the urgency of that creation. There is still deeper darkness ahead, epochs where even Webb struggles to see. But if galaxies were already thriving when the universe was 3% of its current age, then somewhere just beyond that threshold lies the moment when structure first cascaded out of simplicity. And when we reach it, we may find that the universe did not gently evolve into complexity. It may have leapt. There is a point where numbers stop being statistics and start feeling like acceleration. We are there. Because when astronomers began analysing Webb's deepest fields, something subtle but persistent emerged. There were simply more bright, massive galaxies at extreme distances than our best models predicted. Not one anomaly, not two. A pattern. Each tiny red speck in those images represents a galaxy whose light has been stretched for over 13 billion years, its wavelengths elongated by cosmic expansion, shifted deep into infrared. Webb detects that faint heat glow and translates it into structure. And again, we're finding galaxies that appear too luminous for their age. Luminosity matters. Brightness is a proxy for activity, for how many stars are forming, how much mass is locked into stellar cores, how energetically a system is evolving. If a galaxy is bright, it is busy. And some of these early galaxies are blazing. To reach such luminosity so quickly, they must be converting gas into stars at extraordinary rates, sometimes dozens or even hundreds of solar masses per year. For comparison, the Milky Way forms about 1 to 2 solar masses worth of stars annually. These early systems may have been operating at 50 times that pace. Picture an assembly line that doesn't produce 1 car a day, but 50, and it just started yesterday. That's the scale of surprise. Now, luminosity can be deceptive. Young stars are intrinsically brighter. If a galaxy is dominated by hot, massive stars, it can appear extremely luminous even if its total mass is smaller than estimated. As measurements improve, some early mass estimates may adjust downward. But even accounting for that, the abundance of bright systems at very high redshift is difficult to ignore. And abundance is critical. One massive galaxy forming early is intriguing. Many forming early reshapes expectations. Because galaxy formation is not random. It depends on the distribution of dark matter halos, the gravitational wells where gas collects. The number of massive halos at early times is constrained by the physics of structure growth. If we are observing more large galaxies than predicted, then either star formation was more efficient inside those halos, or the halos themselves assembled faster. Neither option breaks physics, but both demand refinement. It's like discovering that a forest you thought would take centuries to mature had already grown dense and towering in decades. Something about the growth conditions was more favourable than assumed. And there is another layer: morphology. Even in Webb's early images, some galaxies appear surprisingly organised, not chaotic blobs, but compact disks, hints of symmetry, even nascent spiral structure. Structure within structure. Spiral arms require ordered rotation. They require gravitational settling and time for angular momentum to shape matter into coherent patterns. If these features truly existed so early, it means dynamical processes were unfolding rapidly. Gas collapsing, angular momentum redistributing, stars forming in patterned flows. It suggests the universe did not just assemble mass quickly, it began arranging that mass into recognizable architecture almost immediately. There is something almost unsettling about that. We often imagine the early universe as turbulent and disordered, a storm of mergers and explosions. And it was. But within that turbulence, order may have emerged swiftly. Gravity does not just clump matter, it organizes motion, it shapes rotation, it creates disks. And in a denser universe, those processes may have occurred on compressed timescales. Now let's widen the lens. The cosmic microwave background shows us the universe at 380,000 years old, smooth with tiny fluctuations. Large-scale surveys today map filaments and clusters billions of light-years across. Between those two snapshots lies the era Webb is probing. The bridge from smooth plasma to structured Webb. If Webb is revealing that this bridge was crossed faster than predicted, then the transition from simplicity to complexity was sharper. Not a gentle slope, a steep climb. And here's the human weight of that realization. We evolved in a galaxy that formed over billions of years. The Sun is relatively young compared to the Milky Way. Earth formed long after multiple generations of stars had enriched the interstellar medium. But if galaxies like ours had precursors assembling so early, then the timeline for chemical maturity compresses. The universe may have been capable of forming rocky planets much earlier than our previous estimates suggested, perhaps within 1 billion years of the Big Bang. That does not mean life existed then. It means the ingredients were available. Carbon, oxygen, nitrogen forged in early stellar furnaces and dispersed by supernovae would have begun accumulating sooner. The cosmos did not linger in sterility for as long as we once imagined. It rushed toward complexity. Webb's data also pushes us to refine how we measure distance and age. Redshift estimates based on photometry must be confirmed with spectroscopy. Some candidate galaxies once thought to be record-breaking have shifted slightly closer upon further analysis. Science corrects itself. But even as specific records move, the broader message remains: early structure formation appears more vigorous than conservative models anticipated. And that vigor matters. Because if the early universe was efficient at building stars and galaxies, then the seeds of everything we know, including us, were planted rapidly. We are not the product of a slow cosmic hesitation. We are the outcome of a universe that moved decisively once conditions allowed. And Webb is still in its early operational years. It will conduct deeper surveys, longer exposures, more precise spectroscopic follow-ups. Each observation tightens constraints, sharpens models, refines understanding. We are watching a feedback loop between observation and theory unfold in real time. Data pushes models. Models predict new observations. Observations surprise again. But through it all, one thing becomes increasingly clear. The early universe was not shy. It did not cautiously assemble small structures and wait. It built boldly. Galaxies blazed where we expected embers. Black holes fed where we expected seeds. Chemical complexity spread where we expected simplicity. And somewhere just beyond our current detection threshold lies an even earlier chapter, where the very first luminous structures emerged from total darkness. When we finally resolve that chapter in full clarity, we may discover that the universe's initial act of creation was not tentative. It may have been explosive in its ambition to sprint into structure that set the stage for everything that followed. There is a deeper tension beneath all of this. It isn't just that galaxies formed early. It's that they may have formed too early, at least according to the most conservative versions of our models. And when something in cosmology appears too early, it forces us to examine the foundation. Not to tear it down, but to press on it. The backbone of modern cosmology is the lambda cold dark matter model lambda CDM. It describes a universe dominated by dark energy lambda, structured by cold dark matter, and governed by general relativity. It has passed test after test. It predicts the cosmic microwave background with astonishing precision. It explains large-scale structure. It accounts for galaxy clustering. It works. But lambda CDM does not specify exactly how efficiently gas turns into stars inside early dark matter halos. That efficiency is modelled with astrophysical assumptions layered on top of gravitational physics. And that's where Webb is applying pressure. If early galaxies are brighter and more massive than predicted, then either star formation efficiency was higher, or feedback weaker, or gas inflow stronger. Or some combination. None of those possibilities violate fundamental physics. They simply mean the universe was better at building structure than we expected. Think of it this way. You design a simulation of a city growing from scattered settlements. You program roads, resource flow, construction rates. You predict that skyscrapers should appear after decades. Then you fly a drone over the real city and see towers rising in half the time. The laws of physics haven't changed. But your assumptions about growth rates need refinement. That's the moment we're in. Some early Webb galaxy candidates were initially estimated to have stellar masses comparable to the Milky Way, when the universe was only 300 million years old. Follow-up spectroscopy has revised some of those numbers downward, reminding us to be cautious. But even after revisions, the density of luminous galaxies at redshifts above 10 remains higher than many pre-Webb models predicted. The early universe appears crowded with ambition. And ambition at that scale implies something powerful about initial conditions. Remember those tiny density fluctuations imprinted in the cosmic microwave background? They were minuscule 1 part in 100,000, but gravity amplifies differences relentlessly. In denser early epochs, amplification happens faster. Small variations become significant quickly. And once the first halos reach a threshold mass around a few million to a few billion solar masses, they can begin efficient cooling and star formation. If those thresholds were crossed sooner than expected in enough regions, galaxy formation could cascade across the cosmos. Not uniformly, but explosively in pockets. There's another layer that makes this even more compelling dust. Even in some early galaxies, Webb has detected indications of dust, tiny grains of carbon and silicates formed in supernova ejecta. Dust affects how we interpret light. It absorbs ultraviolet radiation and re-emits it in infrared. The presence of dust implies prior generations of stars have already lived and died. That compresses the timeline further. Stars form. They explode. They enrich gas. Dust forms. New stars ignite in enriched environments. All within a few 100 million years. That's not just early structure. That's rapid chemical evolution. And inside that chemical evolution lies the raw material for planets. It's impossible not to feel the shift in perspective. We once imagined the early universe as an extended prelude, a long build-up before complexity truly began. Now it appears that complexity may have surged almost immediately after physical conditions allowed it. There is a strange comfort in that, because it suggests that the emergence of structure is not a fragile accident. It may be an almost inevitable outcome of gravity acting on matter in an expanding universe. We are not anomalies in a stagnant cosmos. We are products of a system that accelerates toward organization. But there is still mystery. Some researchers are exploring whether subtle modifications to dark matter behavior could affect early halo formation, Others are refining star formation models under primordial conditions. Still others are re-examining how radiation feedback operates in extremely dense environments. The conversation is alive, and Webb is the catalyst. Every time it stares into a new patch of deep sky, it adds data points to this tension between prediction and observation. And tension is productive. It sharpens theory. It drives creativity. It pushes us closer to understanding how the universe moved from nearly uniform plasma to a web of galaxies in less than 1 billion years. There is something almost poetic about the fact that we're using infrared light stretched and ancient to interrogate our own origins. The photons hitting Webb's detectors began their journey before the Milky Way existed in its current form. They travelled across expanding space for more than 13 billion years, only to end their journey in a telescope built by a species composed of elements forged in those same early stars. We are closing a loop. The early universe built galaxies faster than expected. Those galaxies built heavy elements. Those elements built planets. On at least one planet, chemistry became biology. Biology became consciousness. Consciousness built Webb. And Webb is now looking back to the moment when structure first erupted from simplicity. If galaxies truly formed earlier and more efficiently than predicted, then the cosmos did not inch its way into complexity. It accelerated. And acceleration means we may still be underestimating what else it accomplished in those first few 100 million years. Because if stars, galaxies, black holes, and dust all emerged rapidly, then the early universe was not merely transitioning. It was transforming at full intensity. And somewhere just beyond our current observational reach lies the instant when the first gravitational collapse tipped the balance, when darkness gave way to the first irreversible spark. We are almost there. And when we finally resolve that spark with clarity, we may discover that the universe's earliest chapter was not cautious or slow. It may have been breathtakingly bold. There is a limit to how far back we can see, not because the universe ends, but because light has a beginning. Beyond a certain point, before the first stars ignited, there was no visible light to travel, only darkness not empty, not lifeless, but unlit. Gravity was working, matter was moving, but nothing shone. James Webb is pushing us closer to that boundary than any telescope before it. And as we approach it, something extraordinary happens. The universe begins to feel compressed. Not spatially, but historically. We are used to thinking in billions of years. The Earth is 4.5 billion years old. Complex life has existed for roughly 600 million years. Human civilization spans a few thousand. But the leap from darkness to galaxies may have taken only a few 100 million years. That's the compression. From neutral hydrogen fog to stellar cities in less time than it took multicellular life to diversify on Earth. Webb is identifying galaxy candidates at redshifts of 12-13, even pushing toward 15. That corresponds to when the universe was roughly 300 million years old, perhaps less. To feel that scale, if the universe's age were compressed into a single day, 300 million years would pass in less than half an hour after midnight. Before that half-hour mark, galaxies may already have existed. That changes the emotional geometry of cosmic time, because it means the universe did not linger in simplicity. It crossed the threshold into structure almost immediately after becoming transparent. But here's where the tension sharpens. At extreme redshifts, our measurements grow delicate. Photometric redshift estimates based on how light drops off in certain filters can sometimes mislead. Dust, emission lines, and other effects can mimic extreme distances. That's why spectroscopic confirmation matters. It splits light into detailed wavelengths, revealing precise chemical fingerprints and distance indicators. And as Webb performs more spectroscopy, some early candidates shift slightly closer, records adjust, numbers refine. Science breathes. But even with refinement, the pattern persists. The early universe appears more populated with luminous systems than we anticipated before Webb. which means that even if some galaxies are not quite as extreme as first estimated, the broader acceleration remains. And then there are the quasars. Brilliant, point-like beacons powered by supermassive black holes devouring matter. Some have been found when the universe was less than 700 million years old, already containing black holes with masses exceeding 1 billion suns. To build 1 billion solar mass black hole from stellar remnants requires sustained, near-limit accretion for hundreds of millions of years. There isn't much room for delay. Either the seeds were massive from the start via direct collapse, or growth rates exceeded conservative assumptions. In either case, the implication is the same. The early universe wasted no time assembling gravitational giants. And those giants influence everything around them. Black holes shape star formation. Their radiation heats gas across galactic scales. Their gravitational pull organizes motion. Their presence is not passive. If they formed early and grew quickly, then the architecture of galaxies was sculpted almost from the beginning by these invisible cores. Now widen your awareness. The cosmic web filaments of dark matter stretching across space began forming shortly after the Big Bang. Simulations show that matter flows along these filaments into dense nodes, where galaxies cluster. If Webb is revealing that galaxies were already substantial within a few 100 million years, then those filaments must have been channeling matter efficiently almost immediately. The skeleton of the universe, its large-scale structure, may have solidified early. We are not watching a universe hesitating to organize. We are watching one that locks into pattern swiftly. And inside that pattern, chemistry accelerates. Heavy elements spread through supernova explosions, dust forms, molecular clouds cool more efficiently, star formation cycles intensify. Each generation builds on the last. Within perhaps 500 million years, the universe may have transitioned from pure hydrogen simplicity to chemically enriched complexity capable of forming rocky worlds. That does not mean life flourished then, but the conditions for planets may have been seeded earlier than we ever imagined. It reframes our sense of isolation. If the universe becomes chemically capable of forming Earth-like planets quickly, then the window for habitability opens earlier and wider. Again, not proof of life, but proof that the raw materials for life are not rare or delayed. They are forged aggressively. There is something profoundly humbling about that realization. We evolved late in a universe already mature, already structured, already enriched. When the Earth formed, galaxies had been colliding for billions of years, black holes had grown to monstrous scales, star formation had risen and fallen across cosmic epochs. We arrived in the afterglow of an ancient process. And yet, that process may have ignited with startling speed. The early universe may have resembled a compressed version of everything we see now: turbulence, mergers, radiation, collapse operating on shorter timescales under denser conditions. Webb is not overturning cosmology. It is tightening it. It is forcing us to acknowledge that once gravity had even the slightest advantage, it did not proceed cautiously. It cascaded. And the closer we push toward the first light, the more we sense that we are approaching a boundary event, the moment when the first star ignited and the cosmic dark ages ended forever. When that first fusion reaction began in a primordial core, hydrogen fused into helium, releasing energy that had been locked since the Big Bang. That was the universe's first true sunrise. Everything after galaxies, planets, life traces back to that ignition. And if Webb's revelations hold, that sunrise may have happened sooner than we dared to expect. Which means the universe did not hesitate at dawn. It rose fast. There is a strange irony in all of this. The deeper we look into the past, the more energetic the universe appears. We live in a relatively calm era. Star formation in the Milky Way is steady but modest. Galaxy mergers are infrequent on human timescales. The cosmic expansion is accelerating gently under dark energy's influence. It feels stable, but roll the clock back 13 billion years and stability dissolves. The early universe was a pressure cooker. Gas densities were higher, galaxy separations were smaller, black holes were feeding aggressively, star formation rates were peaking. In fact, the universe experienced what astronomers call cosmic noon about 10 billion years ago, a period when star formation across the cosmos was at its highest. But Webb is revealing that even before that peak, there may have been intense localized bursts, proto-galaxies blazing in compressed space. It suggests that cosmic history is not a straight incline toward complexity. It's more like a surge, an eruption of structure. Let's zoom into one of those early galaxies Webb might detect. It's compact, only a few thousand light-years across, far smaller than the Milky Way's 100,000 light-year span. But inside that compact region, billions of stars are forming or already shining. The density of stellar nurseries is extreme. Radiation fields are intense. Supernova explosions detonate frequently. And at the center, perhaps, a growing black hole anchors the system. From the outside, the galaxy glows in ultraviolet light that is now stretched into infrared by the time it reaches Webb. From the inside, it would be a violent environment, bright, chaotic, bathed in radiation. Yet within that violence lies creation. Heavy elements forged in stellar cores. Shock waves compressing gas into new star-forming regions. Angular momentum shaping rotating disks. Gravity orchestrating order out of turbulence. This is the paradox of early structure. It is violent, yet generative. And the speed of that generation is what unsettles our previous expectations. Because if galaxies of this scale existed within 300 to 400 million years, then the rate at which matter assembled into deep gravitational wells must have been efficient. Dark matter halos would need to grow rapidly. Gas must cool quickly enough to collapse. Feedback processes must not fully suppress further growth. It's a delicate balance. Too much radiation and star formation halts. Too little collapse and structure remains diffuse. The early universe seems to have found a regime where growth dominated. And here's something even more humbling. We're only seeing the brightest survivors. Telescopes detect luminous systems more easily than faint ones. The galaxies Webb identifies at extreme distances are likely the most massive and active among their peers. For every blazing proto-galaxy we detect, there may be dozens or hundreds of smaller, fainter systems just beyond our reach. The early universe may have been teeming with structure at multiple scales, which means our surprise might actually be conservative. Now think about the energy involved. A single supernova releases about 10 to the power of 44 joules of energy, briefly outshining an entire galaxy. Multiply that by countless massive stars exploding in rapid succession. Add accretion disks around growing black holes radiating across the spectrum. Add galaxy mergers compressing gas at hundreds of kilometers per second. The early cosmos was not just assembling quietly, it was releasing energy on unimaginable scales. And yet, all of it governed by the same four fundamental forces that operate today. Gravity pulling inward, electromagnetism governing radiation, the strong force binding atomic nuclei, the weak force enabling nuclear transformations. No exotic new physics required, just extreme conditions amplifying familiar laws. That may be the most astonishing part. The universe did not need new rules to accelerate into complexity. It simply needed density, time, and gravity. And when those aligned, structure emerged rapidly. Webb's observations are forcing theorists to revisit assumptions about star formation efficiency under primordial conditions. They are refining models of gas accretion along cosmic filaments. They are examining how early black hole seeds could form and grow within limited time windows. This is not crisis. It is evolution of understanding. The framework of cosmology remains strong, but its early chapters are being rewritten with sharper detail. And there is something deeply human about this moment. For centuries, we thought the Milky Way was the entire universe. Then we discovered other galaxies. Then we mapped cosmic expansion. Then we detected the afterglow of the Big Bang. Each leap expanded our perspective. Now Webb is compressing our timeline. It is showing us that the interval between simplicity and complexity may be shorter than we imagined. We are witnessing the universe's adolescence, and it appears to have matured quickly. If galaxies were already thriving when the cosmos was only a few 100 million years old, then the first billion years were not empty or tentative. They were foundational. They established the chemical richness, gravitational architecture, and black hole infrastructure that shaped everything after. And somewhere in that accelerated dawn lies the first irreversible ignition, the moment when hydrogen fused in a stellar core for the first time. That moment did not just create light. It began a chain reaction that would eventually produce planets, oceans, atmospheres, and minds capable of wondering about it. We are the distant echo of that ignition. And as Webb continues to peel back the layers of cosmic time, we edge closer to seeing that first chapter in direct detail. The early universe is no longer a hazy prelude. It is becoming vivid. And the more vivid it becomes, the clearer one truth feels. The cosmos did not hesitate to become complex. It surged into it. There is a threshold we're circling now, a moment so early that even Webb's gold mirrors strain to reach it. It's not the Big Bang itself. It's quieter than that. It's the instant when gravity first overcame expansion inside a collapsing cloud, and nuclear fusion ignited for the very first time. The birth of the first star. Before that ignition, the universe had structure and potential only. Dark matter halos existed. Gas was falling inward, but nothing shone, no fusion, no starlight, no supernovae, no heavy elements. Then somewhere, in a dense knot of primordial hydrogen, pressure rose high enough for protons to overcome their mutual repulsion. Fusion began, and light escaped into a universe that had never seen a star. That event changed everything. Because once fusion starts, it is self-sustaining as long as fuel remains. Energy pours outward, counterbalancing gravity. The star stabilizes. It shines. But in those first stars, stabilization was temporary. They were massive, unstable, short-lived. Their lifespans may have been only a few million years less than 1,000th the sun's expected lifetime. They burned fast and died violently. When they collapsed or exploded, they seeded their surroundings with heavier elements and possibly left behind black hole remnants. Those remnants could then merge, accrete gas, and grow. Now connect that ignition to Webb's discoveries. If galaxies appear mature within 300 to 400 million years, then the first stars must have ignited well before that, perhaps within 100 to 200 million years of the Big Bang. That leaves a narrow window. A dark universe for less than 200 million years. Then light. Then explosion. Then galaxies assembling rapidly. That compression is staggering. Because 200 million years sounds vast to us, longer than the time since dinosaurs first appeared. But on cosmic scales, it is almost immediate. The universe became transparent at 380,000 years old. Within roughly 0.2 billion years, a tiny fraction of its current age, it may have transitioned from total darkness to a network of luminous galaxies. That is not gradual. That is a phase change. Like water freezing suddenly when temperature crosses a threshold. Or like sparks racing across dry grass when conditions align. There's another layer that deepens this moment. The first stars likely formed in isolation or small clusters. But once they exploded and enriched surrounding gas, second-generation stars could form more easily. These later stars would be smaller, longer-lived, and more numerous. Which means that within a few 100 million years, the universe may have already hosted multiple generations of stellar birth and death. Layer upon layer of creation. And inside the densest regions, black holes would grow. If direct collapse black holes formed early, their masses could have started at tens of thousands of suns. surrounded by abundant gas. They could accrete rapidly. Each feeding episode releases enormous radiation, visible across cosmic distances. Some of the quasars we observe at extreme redshift are powered by black holes that had to assemble mass at extraordinary rates. This implies that the mechanisms for rapid growth cold gas streams, dense halos, efficient accretion were operating from the beginning. We are watching the universe bootstrap itself into complexity. Gravity builds halos, gas collapses, stars ignite, stars explode, black holes grow, galaxies merge, all within a few 100 million years. And here we are, 13.8 billion years later, deciphering those first chapters through faint infrared light. There is something almost overwhelming about that continuity. The photons Webb captures left their sources before our galaxy settled into its modern shape. They travelled across expanding space for billions of years, passing by countless other galaxies forming and merging, and now they strike detectors cooled to near absolute zero instruments built by a species composed of atoms forged in ancient stars. We are not outside this story. We are its late consequence. If early galaxies formed faster than expected, then the chemical evolution of the universe accelerated. Heavy elements accumulated sooner, dust formed earlier, molecular clouds cooled efficiently. The building blocks for rocky planets, silicon, oxygen, iron may have been widespread earlier than predicted. The cosmos may have been capable of building Earth-like worlds when it was less than 1 billion years old. We don't know if it did, but the capability may have existed. That shifts the emotional weight of cosmic history. We often think of ourselves as emerging near the end of a long, slow process. But perhaps that process was front-loaded intense in its first billion years, establishing the architecture and chemistry that would persist for billions more. Webb is not just extending our vision, it is tightening the narrative. It is showing us that the distance between the first spark of fusion and the assembly of galaxies may be shorter than our intuition allowed. And the closer we get to directly observing those first stars, perhaps through gravitational lensing magnifying their light, or through signatures in surrounding gas, the more we will refine this picture. We are approaching the cosmic dawn, and dawn, by its nature, is abrupt. Darkness does not fade gradually forever. At some point, light breaks through decisively. The early universe may have experienced such a decisive break, a tipping point where gravitational collapse, star formation, and black hole growth surged simultaneously. Webb is guiding us toward that tipping point, toward the first irreversible ignition, toward the moment when the universe stopped being a dark expanse of potential and became luminous. And when we finally resolve that moment in full clarity, we may realize that the cosmos did not tentatively test its capacity for complexity. It embraced it almost immediately. The first light did not flicker hesitantly. It began a cascade that would not stop for 13.8 billion years and counting. There is something almost unsettling about how quickly the universe may have learned to build. We tend to imagine learning as gradual, trial and error, iteration, refinement over long stretches of time. But the cosmos does not learn. It obeys. And when the laws of physics found themselves inside a hot, dense, expanding arena filled with dark matter and hydrogen, they did not experiment slowly. They executed. Gravity amplified tiny fluctuations. Gas collapsed into halos. Fusion ignited in massive cores. Black holes formed and began to feed, all within a fraction of the universe's current lifetime. James Webb is revealing that once the initial conditions were set, structure formation may have been not just inevitable but rapid. To feel that, we need to zoom out even further. The observable universe contains roughly 2 trillion galaxies. Each galaxy contains millions to trillions of stars. Every star is a nuclear reactor converting mass into energy through Einstein's equation, E = mc². All of that complexity emerged from a nearly uniform plasma with slight density ripples. The astonishing part is not just that structure formed. It's that it may have formed quickly. Because speed changes narrative. If galaxies were already well underway within 300 million years, then the transformation from simplicity to complexity was front-loaded in cosmic history. The universe did not spend billions of years in quiet preparation. It ignited. And once ignited, it accelerated. There's another dimension to this acceleration entropy. The early universe was hot and dense, but thermodynamically simple. Over time, as stars formed and black holes grew, entropy increased. Structure formed locally even as overall disorder grew globally. This is one of the great paradoxes of cosmology increasing complexity within an expanding framework of entropy. Webb's discovery suggests that this dance between order and disorder began energetically almost immediately. The first stars were not timid, they were massive and short-lived. The first galaxies were not sparse, they were compact and active. The first black holes were not negligible. Some grew to immense scales astonishingly early. And this matters because it reshapes our intuitive sense of cosmic pacing. We often assume that large things require long times. Mountains take millions of years to rise. Biological evolution takes billions to produce complexity. Civilizations require centuries to develop infrastructure. But under extreme density and gravitational pressure, the universe can build fast. Very fast. And that speed has consequences for everything downstream. If heavy elements accumulated early, then the chemistry of later galaxies inherited that richness. If black holes anchored galaxies from the beginning, then galactic dynamics were shaped early. If cosmic filaments funneled gas efficiently into halos, then large-scale structure solidified quickly. It's like pouring concrete for the foundation of a city in record time. Everything built afterward depends on how fast and how well that foundation sets. Webb is suggesting the foundation may have set rapidly. There is also something deeply human in this moment of discovery. For most of history, we believed we were near the center of creation. Then we realized we orbit an ordinary star in a typical galaxy among billions. Now we're discovering that even our galaxy's early ancestors formed sooner than expected. We are not near the center. We are latecomers in a universe that wasted no time establishing grandeur. And yet, that realization does not diminish us. It connects us. Because the same early stars that Webb glimpses forged the elements that would later assemble into planets and living systems. The acceleration of early structure formation is not an abstract cosmological curiosity. It is the beginning of our material ancestry. Every atom heavier than hydrogen in your body was forged in stellar cores or supernova explosions. If those processes began earlier and proceeded faster than we thought, then the chain of events leading to your existence began almost as soon as physics allowed it. There is something breathtaking in that continuity. From primordial hydrogen clouds collapsing under gravity, to the first massive stars igniting, to galaxies assembling in dense clusters, to black holes shaping their hosts, to generations of stellar enrichment, to planets condensing from dusty disks, to oceans forming on rocky surfaces, to chemistry becoming biology, to consciousness building telescopes that look back. All of it may have been set in motion with remarkable speed in the universe's first few 100 million years. Webb has not broken cosmology. It has illuminated its urgency. And as we continue to collect deeper data, refine redshift measurements, and analyze spectral signatures, we will narrow the timeline further. Some early galaxy estimates may soften, some will be confirmed, but the direction of the story is clear. The early universe was not barren for long. It was dynamic, and that dynamism matters for how we see ourselves. We are not the product of a slow, reluctant cosmos. We are the outcome of a universe that surged towards structure when gravity found opportunity. There is still more to uncover. We have not yet directly observed a first-generation population 3 star. We have not definitively mapped the exact moment when reionization completed. We are still refining how early black holes assembled. But Webb has shifted the emotional landscape. The early universe is no longer an empty preface. It is a chapter filled with rapid creation. And as we approach the final edges of observable dawn, we are beginning to see that the cosmos did not inch into complexity. It leapt. It crossed thresholds decisively. And once it began building, it did not slow down. The light we capture today is the echo of that leap. A reminder that the universe's earliest acts were bold enough to shape everything that followed, including us. There is a quiet shift happening in how we imagine the beginning. For decades, the early universe felt abstract equations on chalkboards, simulations glowing on computer screens, statistical predictions about halos and cooling curves. It was a place of models more than images. Now it has texture. Webb has given the dawn of galaxies shape, colour, brightness. Not in visible light, but in stretched infrared whispers that reveal structure where we expected haze. And texture changes belief. Because once you see something, even faintly, it becomes harder to imagine it differently. We now see compact galaxies blazing when the universe was only a few % of its current age. We see hints of disks. We see emission lines signaling intense star formation. We see quasars powered by black holes that had no business being so large so early, at least according to our conservative expectations. The early universe is no longer theoretical infancy. It looks active, and that visual reality forces a deeper emotional recalibration. For most of human history, the sky was static. The stars were fixed lights embedded in a celestial sphere. Then we learned they were suns. Then we learned they were distant and numerous. Then we learned they formed and died. Now we are learning that the first ones may have ignited faster than we assumed. The cosmos may not have drifted into complexity. It may have rushed. Let's pause and feel that from a human frame. Our species has existed for roughly 300,000 years. Civilization spans about 10,000. Space telescopes are a few decades old. In that blink of biological time, we have extended our vision 13.4 billion years into the past. And what we find there is not simplicity waiting patiently. It is ambition. Galaxies already stacking billions of stars into tight volumes. Black holes already carving gravitational signatures into their surroundings. Heavy elements already circulating through interstellar gas. The universe was building its infrastructure almost immediately. And infrastructure matters. Because once enough heavy elements exist, rocky planets become possible. Once planets form, atmospheres can condense. Once atmospheres stabilize, chemistry can explore complexity. Webb is not telling us that life existed in the first billion years, but it is hinting that the universe became chemically capable of supporting life earlier than expected. That realization stretches the canvas of possibility. If structure formed quickly, then the window for planet formation opened sooner. The cosmic stage was set earlier. Again, not proof, but potential. And potential at scale is powerful. There is another angle that deepens the awe. The speed of early galaxy formation reinforces how finely tuned the universe's initial conditions must have been. Those tiny density fluctuations in the cosmic microwave background, 1 part in 100,000, were just large enough to seed structure, but not so large as to collapse everything immediately. If they had been slightly smaller, gravity might not have amplified them quickly enough to form galaxies before expansion diluted matter too far. If they had been larger, the universe might have collapsed into black holes rapidly, preventing stable galaxies from forming. The balance was delicate. And yet within that delicate balance, structure accelerated. It's like watching a perfectly tuned engine ignite. Not sputtering. Not stalling. But catching and roaring to life. Webb is showing us the roar. And as we refine our measurements, we will determine exactly how early the first massive systems emerged. Some current high redshift candidates may shift in distance. others will be confirmed as record breakers. But even as the details sharpen, the direction is clear. The early universe was not empty for long, and that changes how we feel about cosmic history. Instead of a vast, slow prelude followed by gradual build-up, we are seeing a rapid transformation. From plasma to stars. From stars to galaxies. From galaxies to black holes and chemical complexity. All within the first few 100 million years. It compresses the narrative. It makes the universe feel decisive. And in that decisiveness, there is something strangely reassuring. Because it suggests that complexity is not an anomaly waiting billions of years to emerge. It is a natural outcome once conditions cross a threshold. Gravity plus time equals structure. Add fusion, and you get chemistry. Add chemistry, and you open the door to biology. We are downstream from that equation. Webb is helping us witness its earliest terms. And yet, there is still a horizon beyond which we cannot see. Before the first stars ignited, before any galaxy emitted light, the universe was dark. That darkness is not empty. It holds the seeds of everything. We are approaching it. Each new observation pushes us closer to directly detecting signatures of population 3 stars, perhaps, through the way they ionize surrounding gas. Perhaps through gravitational lensing magnifying their faint glow. When that happens, when we truly isolate the first generation of stars, we will not just be observing an ancient object. We will be witnessing the moment when the universe crossed from potential to expression. And if Webb's early discoveries are any indication, that crossing happened quickly. The cosmos did not hesitate at the brink of light. It stepped forward. And once it did, it built with intensity. We stand 13.8 billion years later, on a planet forged from that intensity, breathing oxygen made in ancient stars, using minds shaped by evolution to decode photons that left their sources before our galaxy was complete. The early universe is no longer a blank chapter. It is vivid, active, and far more ambitious than we imagined. The story is still unfolding. But one truth is already clear. The dawn of structure was not slow. It was a surge. There is a moment when you step far enough back where the entire story feels impossibly tight. 4 forces, a handful of particles, a universe expanding from extreme heat and density, and within a few 100 million years, galaxies. Not faint suggestions of structure, but gravitational cities of stars. James Webb has not just given us earlier images. It has shortened the emotional distance between nothing and everything. Because if galaxies were assembling aggressively when the universe was 300 million years old, then the transformation from simplicity to grandeur happened in less time than it took Earth to develop complex animals. That compression forces us to rethink scale. We are accustomed to believing that the grandest structures require the longest patience. Mountains rise slowly. Species evolve gradually. Civilizations build across centuries. But the early universe had an advantage we will never experience again: density. Matter was closer together. Gravitational wells deepened quickly. Gas did not have to travel far to collapse. The raw materials for stars were packed tightly in a smaller cosmos. Under those conditions, gravity becomes efficient. Not frantic, not chaotic beyond physics, but decisive. And once decisive collapse begins, it cascades. Gas falls inward. Pressure rises. Fusion ignites. Radiation floods outward. Supernovae explode. Black holes form, each step feeding the next. Within perhaps 200 million years, the first stars likely ignited. Within a few 100 million more, galaxies with billions of stars were shining. Within less than 1 billion years, some black holes had grown to millions or even billions of solar masses. And here we are, nearly 14 billion years later, staring back at that sprint. There is something deeply humbling in realizing that the universe's earliest chapter may have been its most energetic. We often think of history as building toward peaks that things become more dramatic over time. But cosmic history may have been front-loaded with intensity. The first billion years were a crucible. Dense, violent, creative. And then, over billions of years, the universe expanded, cooled, and relaxed into the vastness we see today. Star formation rates declined. Galaxies drifted farther apart. Dark energy began accelerating expansion. The cosmos grew quieter. We exist in that quieter era. We were not born in the blaze. We are descendants of it. And Webb is letting us see just how fierce that blaze may have been. If structure formed earlier than expected, then the universe did not meander toward complexity. It lunged. And that lunge has consequences for how we interpret everything that followed. Because the early assembly of galaxies sets boundary conditions for cosmic evolution. It influences how clusters form. It shapes how gas cycles through halos. It determines how black holes and stellar populations co-evolve. It even affects how we interpret the faint background glow left over from reionization. Every early acceleration ripples forward. Webb is not rewriting gravity. It is revealing gravity's urgency under extreme conditions. And that urgency reframes our own place in time. We often think of ourselves as arriving late in an ancient universe. But if the foundations were laid quickly, then we are not simply late, we are part of a long unfolding that began decisively. The heavy elements in your body were forged in stars that lived and died long before the sun formed. Those stars trace their ancestry to even earlier generations, perhaps to systems that Webb is now glimpsing. The acceleration of early galaxy formation is not a distant curiosity. It is the beginning of our material lineage. And there is something extraordinary about the fact that we can detect it at all. The photons Webb captures began their journey when the universe was young and compact. They travelled across expanding space for over 13 billion years, stretching, cooling, reddening. They passed through cosmic filaments, skirted galaxy clusters, survived the birth and death of countless stars. And now they strike a mirror orbiting our sun, a mirror assembled by a species that evolved from stardust. We are not separate from this story. We are its late expression. If the early universe was more efficient at building structure than expected, then complexity is not fragile. It is a natural consequence of gravity given time and density. And that realization does something subtle but profound. It makes existence feel less like an accident and more like an outcome. Not predetermined, but strongly permitted by the laws of physics. The early cosmos did not hesitate to assemble stars. It didn't stall before forming galaxies. It did not delay the growth of black holes. It moved when conditions allowed it to move. And now, as Webb continues to peer deeper, we stand on the edge of resolving the last veil, the direct signatures of the very first stars. When that moment arrives, when we isolate the fingerprints of population 3 stars, when we map the precise timeline of reionization, the narrative will sharpen further. But even now, before that final clarity, we can feel the shift. The universe did not crawl into complexity. It surged. And that surge echoes across 13.8 billion years, culminating in a species capable of asking how it began. We are small. We are late. But we are connected to an early chapter that was anything but timid. The dawn of galaxies was not a whisper. It was a decisive ignition. And thanks to Webb, we are finally watching the universe reveal just how fast it learned to shine. Stand with this for a moment. 13.8 billion years ago, the universe began expanding. For a fraction of that time, it was a furnace, then a plasma, then a cooling sea of hydrogen and helium, then darkness. And then almost immediately, on cosmic scales, light. James Webb has pulled that light back into view. Not the comfortable glow of nearby stars. Not the graceful spirals of mature galaxies. But ancient, stretched photons from systems that should have still been assembling and instead were already shining with improbable confidence. Galaxies with billions of stars when the universe was barely 3% of its current age. Black holes already swollen to millions or billions of solar masses. Chemical enrichment underway. Dust forming. Structure consolidating. All far earlier than our cautious models once suggested. We expected a long dawn. Webb is showing us a rapid sunrise. And here, at the edge of this story, something profound settles in. The early universe was not waiting. It was primed. The laws of physics, gravity, electromagnetism, nuclear fusion did not need billions of years to discover what they could build. They needed density. They needed time measured in hundreds of millions of years, not billions. And when those conditions aligned, structure erupted. From tiny fluctuations in a nearly uniform plasma, galaxies emerged. From collapsing gas clouds, the first stars ignited. From stellar deaths, heavy elements scattered. From dense cores, black holes grew. From enriched material, planets would eventually form. From one such planet, consciousness arose. And now that consciousness looks back, there is something almost circular in that. The photons Webb captures began their journey before the Milky Way existed in its current form. They left galaxies still in their youth. They travelled through an expanding cosmos that would later host trillions more stars. And after 13.4 billion years, they are absorbed by a mirror cooled near absolute zero, orbiting a star that did not exist when they departed. We are intercepting messages from the universe's adolescence. And what those messages say is simple and staggering. The cosmos matured quickly. Not fully, not completely, but decisively. It did not linger in simplicity. It crossed thresholds rapidly. It built. That does not mean our cosmological framework collapses. General relativity still governs gravity. Dark matter still scaffolds structure. Dark energy still accelerates expansion. But Webb has shown us that within that framework, the universe may have operated at maximum efficiency when it was young and dense. The first billion years were not empty. They were foundational. Everything that followed, every cluster, every spiral arm, every planet inherited conditions shaped in that compressed epoch. And that changes how we feel about time. Because if galaxies could assemble so early, then the distance between nothing and something was shorter than we imagined. The gap between darkness and brilliance was narrow. The transition from simplicity to complexity was steep, and we are downstream of that steep ascent. There is humility in this. We are not central. We are not early. We are late witnesses. But we are witnesses capable of reconstructing our origin with extraordinary precision. And that is not small. A species composed of atoms forged in ancient stars has built an instrument that can see the birthplaces of those atoms' ancestors. We are matter, organized enough to ask how matter organized itself. Webb's revelations do not diminish us. They include us. Because if the universe was efficient at building galaxies, it was efficient at building the heavy elements required for life. If heavy elements spread early, the potential for rocky worlds opened sooner. If structure formed quickly, then complexity may be less fragile than we feared. Not guaranteed, but permitted widely. The early universe was bold, and that boldness echoes forward. We often imagine the cosmos as cold and indifferent, but what Webb reveals is not indifference. It is dynamism. It is gravity acting with urgency. It is fusion igniting as soon as pressure allows. It is black holes growing when fuel is abundant. It is a universe that does not hesitate once thresholds are crossed. And here we stand, at the far edge of observable dawn, having glimpsed structures forming earlier than our theories once predicted. The story is still refining. Distances will sharpen. Mass estimates will adjust. Simulations will evolve. But the emotional truth remains. The cosmos did not crawl into complexity. It surged into it. The first stars were not timid flickers. They were colossal beacons. The first galaxies were not scattered whispers. They were compact engines of creation. The first black holes were not afterthoughts. They were gravitational anchors shaping their hosts. And from that surge, from that rapid assembly in a dense young universe, everything else followed, including us. When you look at the night sky now, you are not just seeing distant stars. You are seeing the aftermath of an early sprint, a universe that moved fast when it was young. James Webb has given us that revelation. It has shown us that the dawn of structure came sooner, burned brighter, and assembled faster than we expected. And in that realization there is a quiet, complete awe. We are late. We are small. But we are connected to a beginning that did not hesitate to shine.